Good morning, and thank you for being here. My name is Minerva Vargas, and I want to shortly present an artificial hair flow sensor on a silicon membrane that can be used for flow sensing and haptic exploration. First of all, why are we interested in hair sensors? Well, these sensors can be found overall in nature. For example, here we can see the filiform hairs in crickets that help detect predators, and the lateral line system in fish that they use to navigate. We are mimicking these sensors by using an artificial hair with strain gauges at the base that detect when the hair bends. The model on the left shows a sensor that we presented before that can be used for flow sensing and for haptic exploration, but gets easily damaged. So we propose a new approach using a membrane-based sensor with a silicon column in the middle of the membrane where an artificial hair can be inserted. 4 strain gauges are placed on the membrane around the hair, 2 in the X and 2 in the Y direction. And if the sensor is placed in a flow or a mechanical force is applied on the hair, it tilts, causing the membrane to deform and changing the resistance of the strain gauges. Here you can see a short description of the fabrication process. We start with an SOI wafer as a substrate, where titanium and platinum are sputtered and structured to create the strain gauges and the contact paths. Then, a thin layer of polyimide is spin-coated as isolation. Afterwards, deep reactive ion etching from the top and the bottom side is done to open the contact paths, create the channel for the hair and the membrane. The initial thickness of the membrane is given by the depth of the buried oxide layer, in this case, 20 micrometers, but tests with different membrane thicknesses were carried out. After experimenting with 3 different thicknesses, we determined that the 2 micrometers membrane was too unstable, the 20 micrometer one was too stiff for flow detection, but could be used for haptic exploration, and the 10 micrometer one showed a good response in both cases. So we stayed with this thickness for further analysis. 6 different sensor designs were fabricated, where the diameter of the membrane and the length of the strain gauges were changed. We had membrane diameters of 1.5, 2, and 3 millimeters, each with short and long strain gauges. The small membranes with short strain gauges showed a higher sensitivity. So we used the first one, in this case, 1.5 millimeters with short strain gauges for flow detection. Measurements inside a wind channel were carried out. The sensor was placed on a rotating platform inside the channel and rotated 360 degrees instead of 5 degrees, with a constant flow speed of 2 meters per second. Here we can see the response of both channels where the direction of the flow can be clearly determined. In this case, this was the response of X channel, and the red line is the response of the Y channel. So, as takeaway points, we presented a novel design of an artificial hair flow sensor on a silicon membrane. Using these sensors, the flow direction can be identified. Results regarding haptic exploration and the behavior of the sensors in an array will be shown in future publications. Thanks for your attention. I will gladly answer any questions at the post-presentation.